In this video, we will cover the photoelectric effect. This was an unexplained phenomenon. Classic physics just couldn't handle it. And this really was one of the key experiments and key reasons why quantum physics, quantum theory really began to unfold and take us now to where we are with a relatively comprehensive understanding of quantum mechanics. But the photoelectric effect was right there at the early days of quantum physics. And we're going to need it basically to understand atomic structure and understand more advanced models of the atom. So what is the photoelectric effect? Well, it's the observation that if you shine light on certain materials, electrons will be emitted. So typically it's some kind of metal, and you're shining light. So this is the visible part of the electromagnetic spectrum. We're not applying heat. We're actually just applying visible wavelengths, and electrons are emitted. It's nicely captured by this stamp. I think this is from 1979 by the looks of it. And you can see here some details actually reflected on this stamp, where if you're at the red end of the light spectrum, this is the rainbow, red, orange, yellow, green, blue, indigo, violet. So at the redder end of the spectrum, we have electrons being emitted from this surface here. And you'll notice there's a very small arrow there indicating that there's only a small amount of energy, a certain kinetic energy that's corresponding to this electron coming off this surface. Whereas as you go towards the blue end of the spectrum, you'll see that these black arrows are much larger, indicating for blue light we get a higher kinetic energy of the emitted electrons. So we're going to unpack that and investigate what is going on exactly. So this is a more conventional way of looking at the photoelectric effect. We have a pair of electrodes. We'll call one of them the emitter, and we'll call the other the collector. The reason for that is that we're going to be shining light onto this electrode, hoping for it to emit electrons, and the collector will be collecting those electrons. And notice that, strictly speaking, we don't even need any voltage across here at all. Okay, we've just got a little, basically a way of measuring the current here. And here I'm showing the case of red light, and for this particular material, we have nothing happening at all. And so the first observation is that this photoelectric effect depends on the color or the frequency of the light. So if we now shine blue light, for example, towards the ultraviolet end of the spectrum, the visible spectrum, the blue end, then we get electrons now being emitted from this surface, and some of them will make their way towards the collector. And of course you can always hook up a potential difference between these electrodes, and that can either encourage or discourage those photoelectrons making it across that gap. And so normally also this would be a vacuum in here as well to provide assistance for those electrons making it to the collector. So let's take yet another look at this. This is another configuration, another schematic. We've got blue light coming in onto this emitter electrode here, and we've got electrons being emitted. And it's really, again, a very important observation that there's no potential difference connected up here, and yet we've still got a current flow. And notice actually the current is going downwards here. Okay, we've got the eye indicating current, and the arrow is going that way because the electrons are going in the other direction, because the convention again is that current flows in the direction that a positive charge would move and electrons are negatively charged. But anyway, with no applied potential difference, we actually get a current flow. And so what I've got here is a plot on the right hand side where I've got zero applied voltage here, and yet we are getting a photoelectric current. So I'm indicating that at this finite amount of current here. Now, if we do apply a voltage across here, what we can end up doing is causing more of these emitted electrons to make it across towards the collector. Okay, so with this potential difference, this is going to be a positively charged electrode, and those photoelectrons are going to be attracted towards it. More of them will make it across that gap, and therefore as we increase that voltage, so we draw more and more of those electrons across the gap and they make it to the other electrode, the collector, until we reach a saturation point. And so that's what we're showing here. The collector voltage, that's the voltage here. As we increase it there, so this photoelectric current increases until we reach a saturation point. And that's determined, of course, by the amount of energy being deposited by that light as to how many of the electrons escape from the emitter. Now, to investigate further, what we can do is apply a negative potential difference. So in the green case there, we had a positive so-called collector voltage. Now we're going to apply a negative voltage. And if we apply a negative voltage, now we're trying to attract those emitted electrons back to the electrode from which they were emitted. And so you can see here they're getting pulled back because this is now going to be a positively charged emitter and a negatively charged collector. And so what we can do then is, as we steadily use this negative applied voltage here, we're reducing the photoelectric current until we hit a certain critical voltage where we completely stop the current. And that's going to be a very crucial measurement to make. It's called the stopping potential. How do we stop the photoelectric effect? Or rather, the photoelectric effect is still occurring, but we just stop the electrons from making it across that gap as a means of trying to measure the amount of energy that's been given to those emitted electrons. So that's summarized here. We've got a variable applied voltage V. It can be positive to assist the electrons making it towards the collector. And we also have a negative, we can use a negative voltage to try and draw those electrons back in order to investigate the highest kinetic energy of those emitted electrons. So then, this is the situation. We notice that basically we get emission of electrons in accordance with the frequency or the color of the light incident on that emitter electrode. And we can get more photoelectrons, more electrons emitted by the photoelectric effect by increasing the intensity of that light. And at the same time, though, if we reduce the frequency of the light, in other words, if we go from blue towards the red end of the spectrum, then we get no electrons emitted at all. So that seems easy to understand, just as we list it in that kind of way. But the problem is, in terms of classical physics, this made no sense whatsoever. So what was the classical picture? Well, classically, we would have expected the following, that light waves, I mean, in a sense, you can think of them as a bit like a way of kind of warming up or depositing energy in the electrode. In other words, the light waves are incident on the electrode, they transfer energy as you keep shining the light, and then eventually, when enough energy has been transferred, the electrons are then liberated from the surface. That would have been the kind of classical wave theory of light. And with that picture as well, if we increase the intensity of light, then we would basically increase the kinetic energy of the emitted electrons. But we know from experiment that's not the case. If you've got light at the red end of the spectrum on particular metals, you can make that red light as intense as you like, and you will not get any emitted electrons. And yet if you do a little bit of blue light, ultraviolet end of the spectrum, even relatively low intensity, you get the electrons being emitted. So the classical theory doesn't explain the photoelectric effect. And so that's where Albert Einstein came in, and basically he put forward this equation, which was one that Planck had already put forward in solving another problem, which we'll look at in another video, to do with the black body spectrum. But this was Einstein's solution for the photoelectric effect, was to point out that if we say the energy, or rather if we say that light is not so much waves, but instead photons, packets, wave packets if you like, and if each of those photons has a particular energy that is directly proportional to its frequency. Okay, so that would explain nicely the results that we've seen, because if we had high frequency, so the blue light is high frequency, and this equation says that if it's a high frequency, then it's a high energy, whereas the red light would have a lower frequency and therefore a lower energy. And so that would completely agree with the kind of experimental results that are seen with the photoelectric effect. So this was the equation that Einstein picked up, and it really was nonetheless taken from the work of Max Planck, and we'll look at his formula in another video. But basically it was taking Planck's work, which he kind of put forward as a bit of a mathematical fudge, really. I mean, he used it to fit the data, but he didn't really get a lot of sense out of doing it. And I think there was some kind of desire for that problem not even to be there, but he used it to make the equations work. But Einstein's genius in this was to seriously take this as a real effect, as a real fact, and then apply that to solving the photoelectric effect problem. And then it all made sense. In other words, this was not just some kind of mathematical fudge for looking at emission spectra from light bulbs, but this was actually a necessary equation that is factually the case for physics. Okay, so let's look a bit more then at the mathematics here. So we've got some kind of electrode here, some kind of metal, and it's got some characteristic work function. And what that work function is saying is, what is the amount of energy at minimum that is needed to liberate electrons from the surface? Okay, let's just keep that concept in mind. Then we're shining light onto this surface, and using Einstein's expression, we're saying the energy of each photon of light, I'm showing them here as waves, but now we're kind of saying they're particles, and we'll get into wave-particle duality in another video, but just staying with this for the moment. So we're now viewing these as photons coming in, and each photon has an energy given by hf, where f is the frequency of the light and h is Planck's constant, as Planck was mentioned on the previous slide. And then if we've got the light coming in, we're getting electrons being emitted from this surface, provided there's been a sufficient energy going in, of course, to overcome this so-called work function of the surface. Okay, so at the moment then we've got no applied voltage, and yet what we're getting is, if this is sufficiently high frequency, we're getting electrons being liberated, and some will make it across to the collector and we'll actually be able to record a current even though we haven't applied a voltage. So we're going to say that these electrons have a certain kinetic energy, half mv squared. And then what we can say further is that if a photon has come in with energy hf, and if it's deposited energy that is greater than the work function of the material, then that means the residual energy of the emitted photoelectron is going to have this kinetic energy given by hf, the energy of the photon, minus what was given up to overcome the work function of the surface of the material. So that's just an expression for the kinetic energy of an emitted electron after a photon of energy hf has been absorbed. Okay, now we can apply a voltage here, and that's going to draw in these emitted electrons. Before they were kind of going off in all directions, kind of isotropically, if you like, more or less isotropically within some kind of hemisphere. And now, though, with the applied voltage, they're going to get drawn towards this positive electrode. And then, as we've seen also in the previous slide, we could reverse the polarity and actually do a reverse potential on there and actually stop them from making it to the other electrode. The reason for doing that is that we can now get this nice expression here. If we've succeeded in stopping every last electron from making it across the gap there, then that means the maximum possible kinetic energy of any particular electron at best would have been matched by our stopping potential, V0, multiplied by the charge of an electron, because this is the potential energy, okay, that is set up between these two plates with a stopping potential of V0. And we're just doing, again, that classic equation between kinetic energy and potential energy. And we're saying if we've stopped them from making it across there, then that means all of that potential energy is matching the maximum of the kinetic energy. And then from the previous slide, we've already seen that the kinetic energy is given by HF minus the work function. So that's explaining this expression here. So I've just clarified on the slide here, the stopping potential V0 is the reverse potential needed to stop all the electrons. And we need that to match the highest kinetic energy of any emitted electron to completely stop all the current flow. Right, so a bit more detail then. So you'll recognize this kind of curve from an earlier slide where we've looked at the photoelectric current on this y-axis here, and then we've got the applied potential on the x-axis here. When there's no applied potential, we do get current flow. And now to point out what happens if we increase the intensity of the light. So if we double the intensity, if originally it's intensity I, if we double that intensity, then we do get double the current flow, which might be expected. But it's very important to note that the stopping potential remains the same. In other words, even if we just, multiply by 10 the intensity of the light, seeming to put in lots and lots of energy, nonetheless, if we just tweak that stopping potential to just that right amount, then whatever the intensity of the light, we can still stop the photocurrent. So that also is quite an impressive effect. So there's actually a hard cutoff here with that stopping potential V0. Now though, if we change the frequency of the light, so in other words, if we go to a higher frequency light, that will necessitate a more extreme value of the stopping potential in order to stop the photocurrent from flowing. So increasing the frequency of the light means a greater stopping potential is needed, whereas if we change the intensity, it has no impact on that stopping potential. So again, these are really key graphs for understanding what is going on with the photoelectric effect. So what we can do, this is the last slide, is explore the behavior with respect to stopping potential. So, and this will allow us to find the work function of a material as well as to find what is Planck's constant, that scale factor that relates energy and frequency for a photon. And so that's what I've got here. I've just plotted a stopping voltage on the y-axis here and then frequency of light along this axis here. So what you could do is just explore different frequencies of light. So you could do that by doing different color filters. If you've got some kind of white light, you can use different monochromatic filters to just have particular colors of light coming through. That allows you to change the incident frequency, f, so that's on this x-axis here. And then for each of those values of f, we can then tweak that applied voltage and find what is the voltage necessary to stop the current flow. And so if you do that, you'll find that you get this linear relationship here, saying that as you increase the frequency of the incident light, so you need a greater and greater stopping potential. Okay, that ties in with all that we've just been saying earlier. And then with that, if we do a number of points of this with a number of different colors of light, we can then, in fact, extrapolate that line back here, and that will actually indicate the work function of the material. Why is that? Well, this is just a linear relationship. We're saying that this is the stopping potential V0, and we know that that's the potential energy that we looked at in the previous slide. It's just EV0, and we know that that's going to match the maximum kinetic energy of any emitted electron, which we know is going to be HF, F the frequency of the light, multiplied by Planck's constant, minus the work function phi. So you just need to visualize this as a kind of y equals mx plus c. So if we've got V0 on this y-axis, then then that means over here we could do h divided by e, and that would be the gradient of the frequency f minus phi divided by e. It depends how you choose to do your linear plot. But the point is, we're just trying to find two values here, Planck's constant h, which is the gradient of the line, and then v0, which is related to the intercept on the y-axis. And so if you do that, and here's an example of the kind of plot that was in fact done many, many years ago, you can come up with an estimate of Planck's constant. And the modern day value is given by 6.626 times 10 to the minus 34 joule seconds. And that makes sense, of course, because E is energy in joules, and so therefore Planck's constant must be joule seconds because frequency is per second in hertz. So if you do this for various materials, as shown here, you can find typically what that intercept phi, the work function, is. And I'm quoting values here. They're typically in the EV range. So that's all I wanted to cover on the photoelectric effect. And the real takeaway formula from this video is that the energy of a photon is equal to Planck's constant multiplied by the frequency of that light for that photon. Because we're going to be using that as we move forward to more advanced models of the atom. Thanks for listening.